Good morning to all of you. I welcome you to the third day of our online course. And we have with us today Professor Tandon. He'll be speaking to us on research methods in mathematics. Professor Tandon obtained his PhD from Lang University under the supervisorship of under the in Yale University under the supervisorship of Professor Langlands. Professor Langlands is the winner of 2018 Abel Prize. It's one of the most prestigious prizes for mathematicians. Professor Tandon works in an area of mathematics which is now called the Langlands program. After his PhD, he joined TIFR and then at Nehru University as a reader. He left Nehru in 1978 to join University of Hyderabad, and since then has been there. He has about 41 years of experience. He has guided 9 PhD students. The last of his PhD students received in 2018. He has visited Oregon University, Institute of Advanced Studies, Princeton, Simpa School in Nice, France, University of Sydney, ICTP Trieste. He was a visiting faculty at Triple IIT Hyderabad for over a decade. He has some interest in number theoretical aspects of cryptography. And the good news is in 2020, one of his students, Dr. Ananthvardhan, received the prestigious Shanti Swarup Bhatnagar Award. So we are privileged to have you, sir, with us. And I hand over to Professor Tandon to talk on the research methodology on mathematics. Thank you, sir.
Thank you, Professor Hassan. Uh, I thank Manu for calling me for this. It's a new experience for me. It's the first time I'm on Zoom, and the first time I'm speaking on a topic like this. Actually, I would have liked to rephrase my topic. I'm going to be talking more about problems of research in mathematics. Uh, since there's no data involved here, I'm actually talking about pure and applied maths, not statistics. And even the applied math that I'm talking about is not engineering, it's basically differential equations and just mathematics. So, research methods, they must meet some criteria depending on what your purpose is. But the maths that I'm talking about, the only criteria it needs to meet is that it should be logical. Whatever you prove should be a valid proof. And this 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 idea that it should be a valid proof. Um, just 1 minute. Uh, can sometimes be a little tricky idea. So the first, let me talk a little bit about validity and logic in mathematics. We all seem to have some intuitive notion of what is logically correct. Uh, I think a kid has a certain sense of logic untaught. Uh, I think it's somehow built into us. Um, but sometimes our intuitive notion of what is logical can be a bit misleading. Um, it's something like definition of God. God can do everything. So the question that is immediately asked is, can he build a wall that he cannot climb? this kind of ambiguity, this, it can be given a mathematical context. So let me, there's this very famous contradiction that was enunciated by Russell and Whitehead. And let me just say a few words about that, just to show how tricky logic can be. This concept of a set of sets can be a very tricky concept. So what Russell did was he defined a set to be extraordinary if it is a member uh, of itself. This thing is if it is a member of itself. Just let me. Yeah, if it is a member of itself. Uh, Now, this sounds very odd, but let me give you an example immediately. So, your set is going to be a set of sets because it has to be a member of itself. So, its members should also be sets, right? So, look at this example, the set of all sets which can be defined in the English language in less than 100 words. Now, this set itself has been defined in the English language in less than 100 words. So, therefore, this set is a member of itself. Now, this is a really corny concept. Okay. So, uh, a set is said to be extraordinary if it is a member of itself. So, its members are also sets. Uh, any set which is not extraordinary, I'll call it ordinary. So, these two concepts are mutually exclusive. Something has either to be ordinary or to be extraordinary, because the one is just the negation of the other. All right, so the question that's asked is, if I let X be the set of all ordinary sets, is X ordinary or extraordinary? If I let X be the set of all ordinary sets, is X ordinary or extraordinary? If X is extraordinary, then it has to be a member of itself, but its members are all ordinary, so it can't be extraordinary. On the other hand, if X is ordinary, then since X is the set of all ordinary sets, the stress is on all, X will have to be a member of X, and therefore it will be extraordinary. So whichever way you look at it, it doesn't seem to be either ordinary or extraordinary. It's something equivalent to that argument on God that I had given. So, so you see, this idea uh, of what is logical, I mean, this concept of extraordinary set, once you see the example, doesn't seem to be at all, you know, at all non-intuitive, but it, it, it became very clear to Russell and Whitehead that the concept of set of sets, and particularly some universal concept of set of sets, is a dangerous concept. It will lead to contradiction. And therefore, uh, they tried to get around this by putting some restrictions on set theory. Uh, they came up with some theory of descriptive sets, but logicians were never fully satisfied with what their solution was. But I don't know how many mathematicians there are in the audience, but there are sometimes something obvious is equivalent to something non-obvious. Let me give you an example of that. My example will be from what they call mm, axiom of choice. and Zoneslemma. These are these are absolutely fundamental things to any mathematician. Uh, I don't know, maybe even the physicists may know about him. So basically, what the axiom choice in essence says is that if you have a set and you look at its family of subsets of that set, then you can basically choose one element in each member of the subfamily of subsets. So suppose I have a set and I have a family of subsets of this set, then I can choose a new set by taking just one member from each member of the family. Now that seems to be intuitively, like if sometimes I mention it to a kid and he says, yeah, that's obvious. But the fact of the matter is that this is really not so obvious because it's equivalent at least to something which is not so obvious. And what is that? That's Zoneslemma. What does Zoneslemma say? Zoneslemma says that if I have a partially ordered set, uh, a set which has an order on it, but it's partially ordered in the sense that two, suppose I call is less than or equal to that's my order. Then it's possible that two 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 members of the set may not be comparable at all. That's the partial order. Uh, so if I have a partially ordered set, then if I take a chain in that set, a chain is a totally ordered subset. Totally ordered subset is one where the any two elements are comparable. So all chains have an upper bound. Uh, then this partially ordered subset will have partially ordered set, will have a maximal element. Now this is quite technical. It's about order and all that. But it turns out that the axiom of choice and Zone's lemma are equivalent to each other. Each implies the other. So you see, something which seems to be obvious can be equivalent to something which is quite non-obvious. So, you know, I'd like to mention one more thing in logic till I move out of logic. Um, Sometimes you get solutions which are very odd to problems. Uh, Let me give you an example. My example is that of the continuum hypothesis. So let me mention that again. Continuum hypothesis. So let me say what this was. Um, if a set can be put into bijective correspondence with the natural numbers, then we say that the set has cardinality aleph naught. Okay, cardinality aleph naught if the set can be put into bijective correspondence with the natural numbers. And if a set can be put into bijective correspondence with the real line, then we say that it has cardinality C. C stands for continuum. C stands for continuum. So if a set can be put into bijective correspondence with the natural numbers, we say that its cardinality, it's a kind of a measurement of infinity. Its cardinality is aleph naught. Whereas if a set can be put into um, bijective correspondence with the real line, then we say that the set has cardinality C. C stands for continuum. Now, it was a long-standing question at the turn of the last century. These concepts were enunciated by Cantor. Yeah, the problem was, is there a cardinality between aleph naught and C? That was, now what do I mean by between? Yes, I should explain that. If I can have a function between two sets, A and B, which is one to one, but not onto, and I don't have a bijective function. I could have another function which is bijective, but no, there's no bijective function between A and B, but there is an injective function from A to B, injective. Then I say that the cardinality of A is less than the cardinality of B. So you have, by these injective functions, you get this order notion amongst cardinalities. So if there's no bijective function between A and B, but there is an injective function from A to B, not necessarily surjective, then not surjective, I should say, then I say that the cardinality of A is less than the cardinality of B. It is quite intuitive. So the question was, is there a set with a cardinality between aleph naught and C? Is there a set between, so in other words, can I find a set A? Can I find a set A? Does there exist a set A such that there exists injective F from the natural numbers, N stands for natural numbers, to A, and injective G from A to C, to the real line. So these are injective, not surjective, not surjective, not surjective. So is there a cardinality strictly between, hello? Is there a cardinality strictly between aleph naught and C? And it was felt that there's no such cardinality. That came to be known as the Continuum Hypothesis. But finally, in the 60s, in the mid 60s of the last century, Professor Cohen of Stanford came up with a solution. And the solution was extremely funny. What he showed was that the continuum hypothesis is independent of the Zermelo axiom system. We have a axiomatic system for set theory called the Zermelo axioms. That's normally accepted by all mathematicians. And he showed that this continuum hypothesis is independent of this. You can neither prove it nor disprove it. So you would have a perfectly consistent system of logic if you assumed that the continuum hypothesis is true, but you'd also have a perfectly consistent system if you assumed it is not true. It was independent of the Zermelo axioms of set theory. So you see, sometimes, this kind of thing can also happen. But these are all esoteric things. I mean, mathematics can be strange sometimes, but normally the kind of mathematics that we do, we have an intuitive notion of what is logical. We don't bother about all these things, but it's good to know that these kind of problems do exist in axiomatic systems. All right, so I want to mention one more thing. See, in research, you either search for a new formula, a new result which you guess at, or you don't guess at. It's just a shot in the dark, and you just arrive at a result, and you never guessed at it, but you just arrive at it. some kind of formula usually. Sometimes you guess something is true and try to proceed in trying to prove it. Okay, so that's you conjecture. The word is conjecture. You conjecture that something is true and then try to prove it. Uh, but sometimes, very funny things can happen. Even in this kind of logic. Uh, and the most famous example of this is the example of format primes. Let me just mention. So format primes. For, for a long time, mathematicians were searching for a formula which would give primes. Uh, for a long time, mathematicians have been searching for a formula which would just generate primes. And Fermat had suggested that if you look at 2 to the power of 2 to the power of t plus 1, where t is either 0 or any natural number, then this is always a prime. So if I put, for instance, t equal to 0, I get 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 plus 1 is 3. So I get a prime. If I put t equal to 1, then 2 to the power of 1 is 2, 2 to the power of 2 is 4, plus 1, that is 5, which is again a prime. If I put t equal to 2, then 2 to the power of 2 is 4, 2 to the power of 4 uh, is 16, 16 plus 1 is 17, which is a prime. For 3, you will get 257. For 4 also, you will get a prime. Now already, Fermat had suggested this. So this is, more than 350 years ago. He had no computers. So having done up to 4, he just thought that this is always a prime. And he conjectured that this formula 2 to the 2 to the t plus 1 will always be a prime. Well, it turned out that for t equal to 5 already, the first case that he had missed out, it turned out not to be a prime. Uh, something like some 617 or something like that is a factor for t equal to 5. And then once we had computers, the benefit of computers, and we could do massive calculations, people started uh, making computations for higher and higher t's. And as far as I know, we have reached up to t equal to 30 approximately. We know the status of this problem up till t equal to 30. And the interesting thing is that from 5 to 30, t equal to 5, 6, 7, 8, right up to 30, none of them is a prime. So you see, the conjecture has been turned upside down. None of them is a prime. In fact, when it was first shown that for t equal to 5, it's not a prime, they thought, okay, maybe there are a few exceptions. Sometimes there are exceptions. But now it turns out that for all values of t up to 30, which is, beyond 30, the number becomes too large for us to determine whether it's a prime or not. none of them is a prime. So the conjecture has been turned on its head, and we now perhaps believe that beyond the first few values of t, it's never a prime. So this is another funny thing uh, that can happen. But this is a, you know, this is the way research is done. You either search for a formula or you have a hunch about what is true in a particular situation, and you try to prove that. In so like when I was working with my PhD students, I would my normal method used to be I would look for a question asked in a paper in a good journal. Uh, Professor Hassan had mentioned I worked in something called the Langlands program. So there are just hundreds of problems in this program. And there are lots and lots of people who are working in this area. So uh, I would I would be, you know, very often in when somebody published a paper, they would at the end of the paper ask some open questions. There always be open questions left. That's the nature of mathematics. That the more you know, the more there is to know. So uh, and I would often choose one of these questions and give it to my student. The one thing that you really have to be careful of is that it should not be too hard. I mean, I know, for instance, that the Riemann hypothesis is an open question, but certainly I wouldn't give that to my student. Um, so, yeah, usually research students have three types of mentors. Um, I've known actually all three type of mentors. Uh, there are those who will either suggest a problem to you, something that they've not been working on, and something they're interested in the answer, and they suggest the problem to you. There are even those who don't even suggest a problem to you. They just suggest an area to you and ask you to pick up a problem in that area. Those are the really hard mentors. And then, of course, there are those who actually are working on a problem, and half the problem is done, and then they give it to their student and say, "Look, why don't you finish it?" Um, so so a student could enter a research problem in one of these three possible ways. There's one question that often arises, and that is about the quality of a problem. This is a really, really controversial and subjective matter. I was once talking to the president of the International Mathematical Union. He was a Oxford professor called Sir John Ball, and he asked me, should Princeton and Paris always set the standards? Uh, Actually, he was a very pro third world person. His own wife was Indian Tibetan, and he he said this question he asked me: should Princeton and Paris always set the standards? You know, there's always this question of a good problem. what is a good problem? Uh, this is one of the very central things in research in mathematics. It should not be too trivial, an exercise which students, which a beginning student could solve. So it should not be too trivial. But should it be the following type, for instance? I once knew a professor. He used to work in point set topology, and he used to keep on defining different concepts of compactness. Just this type of compactness. He had some 10 different definitions of various types of compactness. And then he would keep on publishing papers about, which implies what, which doesn't imply what, and so on. So there are, you can sort of create an area for yourself and keep on moving around in circles in that area. Normally, an area of mathematics is considered rich. The more connection, two things I should say. First of all, mathematics, at least I believe, but maybe not everybody believes this, should satisfy the property of beauty. There's something, there should be something beautiful about it. Now, this is very strange. As Professor Raghunathan says, mathematics is more an art than a science, and this is supposed to be research methodology in science. You will normally find mathematics in schools of physical science. So it's normally associated with science because it's used so much in science. But actually, it's a matter of aesthetics to many. The more simple and beautiful an argument is, the more the more it would be considered as good mathematics. Let me give you an example of what is considered to be a simple, beautiful argument. Let me give you an example of that. Any kid up to the 10th class learns what is known as the fundamental theorem of arithmetic. Of course, it may not be told to them that this is called the fundamental theorem of arithmetic, but basically what it says is that every natural number larger than 1 is either a prime or a product of primes. Okay. Every natural number larger than 1, not equal to 1, is either a prime or a product of primes. So the question that was asked by Euclid was, are there finitely many primes or infinitely many primes? And he came up with a beautiful proof of contradiction. So he said, let us assume that let P1 to Pn be all the primes. So we are assuming that there are only finitely many. Then he says, look at 1 plus P1 into P2 into Pn. That is, take the product of those primes and add 1 to it. And by the fundamental theorem of arithmetic, this is a product of primes. But the only primes are P1, P2 to Pn. And none of these primes divide this number because they all give the remainder 1 when you divide by any pi. So therefore, I have a contradiction to the fundamental theorem of arithmetic, and there cannot be only finitely many primes. So this is Euclid's argument. It's really quite a beautiful argument, and it's so simple. Of course, our state of knowledge now is so deep that it would be difficult to say some given examples which is that simple, but still it needs to meet the criteria given the state of knowledge that we have of simplicity and beauty. But if it is going to be applied somewhere and you know beforehand that engineers or computer security people or some are searching for something in this line, and you go and prove something in that line, well, then it has that sort of mathematics has the obvious quality of usefulness. But the funny thing is that if you go to Princeton and Paris, a lot of the mathematics doesn't obviously seem to have the quality of usefulness. So should we reject it? Should we define different types of compactness? And this brings me to another point. The referral index, how many people refer to you. This in mathematics, this is often considered a sign of how productive and how useful your research is, but it's in mathematics is a total misnomer. It's completely ridiculous. See, that's the problem with trying to have a fit-all solution for all subjects. It doesn't work. You don't have, a fit-all solution for all subjects will not work. Because what is happening today is that, a group of about 40 people are doing some trivial work and keep on referring to each other and, mentioning each other in their bibliographies. And so this index, they make it high. Whereas if you take a journal like the Annals of Mathematics, now to the non-specialist, I should mention that the Annals of Mathematics is a journal which is published by the Institute for Advanced Studies at Princeton. And it has a very unique place in mathematics. In the sense that it's the undisputed number one. They claim that they publish only seminal papers. The word is seminal. That is, it's going to be the core of something new. And so it has this preeminent place in journals. But the papers there are so hard that very few people read it. So if you publish there, the referral index will be very, very, very small. Though it's, like the kind of papers that are published in it are all path-breaking and very often, for instance, Wiles and Taylor proof of Fermat's last theorem was published in the Annals of Maths. Or in cryptography, the Manindra Agarwal, Kayal and Saxena proof of the fact that there is a polynomial time algorithm to determine a prime was also published. These kind of very, very seminal papers, almost all the papers of Harish Chandra uh, setting up the theory of semi-simple Lie groups were published in the Annals of Maths. So, it has a very special thing. But, the number of people who can read a paper there is very few. So, you if you publish there, your referral index may be very low, but it may be a very, very high quality work. So, this kind of thing doesn't always work. Uh, I should mention one more thing, that what is a proof? This idea is is slowly changing, and I want to give two examples of this, of what is a proof. If 50 years ago you had given a proof of some result using computers, well, 50 years ago they were not there, but using calculations uh, of the type that a computer does, you would have been scoffed at. But look at this problem, which is called the four color problem. The four color problem. So what does this problem say? So let me, sorry, this is supposed to be a circle, and there's another circle inside it. So, suppose in a region in a circle, um, I divide it into four sub-regions as indicated in what I have drawn. You can see that I require, every region touches three others. Every region touches three others. So if this was a map of, four different countries, then, and if I wanted to color the map in such a way that two adjacent countries do not have the same color, then I would require four colors for this map. And the conjecture was that no matter what map you have, uh, four colors would suffice. Okay, so this is an example where four colors are required, and you never require a fifth. I mean, no matter what map you have. I should, of course, clarify here that point boundaries are not allowed, right? A boundary should always be an arc. A boundary should squiggly, curly, whatever, but point boundaries are not allowed. So four colors suffice. This was basically a problem in graph theory. Uh, because, you can, whether the boundary is squiggly or, you could always replace it by a set of small, short lines. The nature of the boundary for this problem doesn't really matter, except that it should not be a point boundary. Um, so, yeah, so this was a problem in graph theory, and people used to associate various invariants with a graph. Okay, I mean, I won't go into what the invariants were because that would lead to too much technicality. But usually they associated various variants, some number associated with the graph. And normally the invariants were such that the number of graphs, possible graphs with a given invariant is finite. Okay, there was not just one concept of invariant, there were several concepts of invariant. But normally they were characterized by this, that the number of graphs, possible graphs, of course, there's a notion of equivalence of graphs. I mean, if I have a curved line and a straight line boundary, it doesn't really affect this problem. So from a point of view of the four color problem, those graphs are equivalent. So uh, the number of graphs or graphical types with a given invariant was finite. And then there were these two mathematicians at Illinois, uh, Apfel and Hanken, who showed that if the invariant of a graph is large enough, if the invariant of a graph is large enough, some invariant they were looking at, then four colors suffice. Now, this is something very strange that can sometimes happen in maths. So to all graphs, they associated invariant. The number of graphs, equivalent graphs, let me say, with the same invariant is finite. If the invariant of a graph is large enough, greater than equal to some n, then four colors suffice. They managed to prove that. So then it became a question of looking at all graphs with lesser invariant. Okay, so if the invariant is more than n, say, then four colors suffice. So therefore now we need to only look at graphs whose invariant is less than n. So 1, 2, 3 up to n minus 1. And for each such graphical type, there are only finitely many graphs. So the total number of graphs whose invariant is less than n is finite. And then they made out a computer program and looked at all these finite, the number is large and they many days of computer hours they took, but they looked at all the graphs with lesser than n invariant, and for all of them, they showed that four colors suffice. And therefore, the four color problem was solved. So this was a new element in mathematics where you don't have just a final proof, you have a proof together with a computer calculation. And, there are several mathematicians who find this unsatisfactory. And, and quite a few people have made it their aim to give a purely mathematical proof without using computers. Another thing that can happen in research is in mathematics, and I will talk about that, is a huge collaborative effort. I think this perhaps happens in other subjects as well. And the primary example of that is the classification of finite simple groups. So, classification of finite simple groups. Yeah, so I don't know how many of you know what is a group. You have a set and binary operation like multiplication addition on the set, and this binary operation satisfies a few three properties. I won't go beyond that. I don't want to bore the non-mathematicians. So and then you have something called a normal subgroup. You have a group and a subgroup and a normal subgroup. And a group is said to be simple uh, if it has no proper non-trivial normal subgroups. That was the statement, definition of a simple group. And In the last century, some examples of simple groups were known. Uh, they were matrix groups. So they were sort of n by n matrices with elements in a finite field. So that it becomes a finite group and satisfying some properties. And these, these, these groups were found to be simple. They came to be known as the Chevalier groups associated with matrices. Then, near about the First World War, or a little bit earlier, um, there was this British mathematician called Matthew who discovered 5 simple groups. They came to be known as the Matthew groups, which which were simple. They were finite simple groups. And then throughout the teens and the 20s and the 30s, 40s, 50s, people kept on discovering odd simple groups. They were large order. They were of large order. The last such simple group that was discovered came to be known as the monster group. It was a very large order, but it was simple. And then I don't know what came over this world of finite group theorists, what came over them. Clearly, the experts could see something intuitive. It was telling them that they had exhausted all simple groups. They knew all the finite simple groups. There were no more. I mean, this is a really bold assertion to make. You, in fact, these other groups like Matthew group and Leon group and the monster group, they were all known as sporadic simple groups. They were the sporadic, they occurred sporadically. And finally, there were 26 sporadic simple groups. And then there were those matrix groups, the Chevalier groups, and there was also the alternating group AN. Whatever. Suddenly, the group of experts in this area who work in group theory, they felt that there are no more simple groups to discover, that all of them have been discovered. Now, it's pretty hard to prove a result of this nature, that nothing, no more exists. That if you take any finite simple group, it has to be isomorphic to either one of the 26 sporadic simple groups. And, they were all of different order. So if you knew that they are isomorphic to one of the sporadic simple groups, then you knew, and if you knew its order, then you knew which one it is isomorphic to, or it's one of the Chevalier groups. And in the early 70s, I was a graduate student then, there was a big conference of some approximately 15 of the top experts in finite group theory. I think they met in Boston, if I'm not mistaken. And they chalked out a plan of how to prove that the list of simple groups which they had were all. That any simple group must be isomorphic to one of them. It was a massive plan which required lots and lots of little pieces to be built up and little theorems to be proved. And the different experts in, each one of the 15 was an expert in something different from the other. They allotted pieces of the jigsaw puzzle to these experts. you try to prove this, somebody else, you try to prove this. And so they set up with this aim of finally proving the total classification of finite simple groups. And it was amazing that in half a dozen years, by 1978, they had the classification. They had proved that result. So their hunch that these groups were the only ones was correct. This is an example of a huge collaborative effort where a seminal theorem is obtained by the brains of several. So this is another thing that can happen in uh, mathematics. Uh, yeah, I've actually not really come to any solution about the problem of uh, the quality of a problem, the quality of a paper. But this is a matter that needs to really be looked at because there's such huge variation in standards that the National Academy of Science in India has actually been forced to create a category of journal called junk journal. Uh, and as luck would have it, uh, the vast majority of junk journals are either published from Hyderabad or Andhra Telangana or Delhi. Delhi also is a big center where uh, these junk journals, uh, often you just have to pay 500 rupees or some amount of money and get it published. They are, like many of the junk journals are full of wrong results. Uh, or many of the junk journals are full of trivial results. Like you give some long argument to prove something, whereas actually there's a 2-3 line proof argument which proves the same thing. So, so there was a time when people felt that this this problem is purely subjective. Uh, what Princeton and Paris need not set the standard. There can be a lot of good problems even otherwise, or you can just play around in circles with definitions of compactness or something like that. It was easy to judge a problem if it was very obviously useful in some applied area. Then it met the criteria of usefulness and it would not be questioned. And I'm looking at valid problems with valid proofs. I'm not looking at these wrong proofs and complete rubbish that is published in some of these so-called junk journals, a category created by the National Academy of Science, Indian National Science Academy, sorry, INSA. Uh, but the problem has really become serious now. And we really need to think of, in research, what is a problem worth doing? I was so bothered by this that I almost always chose for my students, as I mentioned before, a problem that was asked by a person well known in the field in some article of his, some paper of his or her. Right, you at the end of the paper you find, I'd like to know, what is the situation if you generalize like this, or what is the situation if you do this. And And these seem to be good problems to do because clearly there were people in the mathematical world working in my case, the Langlands program, who were interested in the answer to uh, the question that they had asked. But and it's now reached. This problem has now reached the selection committees. Even like, do you know? Do you have only papers in junk journals, or do you have papers in refereed journals? Usually, if a paper is refereed, it's likely may not be so much junk, but even refereed journals, and in fact, already these junk journals have become wise to the situation and have started calling themselves refereed. But then you referee a junk paper by an equally, but another person who writes a junk paper. So this has really become a problem. So, but you know, to give you a definition of a paper that is useful, not junk, but does not meet the criteria of usefulness. And usefulness actually need not even be in an applied area. Usefulness could also mean in some other mathematics, right? You can use this. You can use this result that I have proved in such and such a situation. Other, in fact, the more connections a paper has into different areas, the richer it is considered. Uh, so, for instance, like in the annals of mathematics, they will have only papers with connections with several areas of mathematics. Usually, the Agarwal Kayal Saxena paper was not like that, but you seldom find a purely algebraic paper. Uh, there are some pure algebraic or group theoretic papers in the annals, but they are very few. They consider something seminal uh, if it has rich with connections to different areas of mathematics. Uh, so, I can't give you a definition of what is a good paper, uh, what is a reasonable paper. It's if you're in the area and you get a feel for it. Uh, but otherwise, I can't really, give you a point blank definition of what is a good paper. If you're fortunate enough to have been trained well in mathematics, then you will understand it by yourself. Uh, and the thing is that there are a lot and lot of mathematics which doesn't really seem to satisfy the criteria of usefulness, except in that area itself. One question asking another, and so on. That way, you could connect up, but so you know, I should mention in this context, Professor Abhyankar. He was an algebraic geometer. Uh, he was a professor at Purdue. He passed away a few years ago. Uh, and he was an algebraic geometer, but algebraic geometry has now become extremely abstract. Categories and functors and schemes, and it's really become extremely abstract. But you know, when, when, when you look at it and you see that some very, very important theorems this kind of mathematics has helped us to prove, then you realize that this abstraction is not just for the sake of abstraction. These are actually extremely useful concepts, though they are very abstract. But Abhyankar kept on maintaining that algebraic geometry should be understood by a school kid. And I will never do any algebraic geometry which goes to such abstraction. And the thing is that his algebraic, he was a student of Zariski, and his algebraic geometry was not trivial. Uh, but you see this, so you see, he questioned Princeton and Paris. I mean, basically, that's the whole point. He questioned Princeton and Paris because this new abstract geometry was started by this French mathematician in Paris called Grothendieck and developed a lot at Princeton also. So Princeton and Paris need not set the standard. I don't really have a problem, but clearly there is a concept, there is something called junk papers, and one should be careful of them. Um, One last thing I'd like to mention. This is really, really strange. You know, we have a belief that what is logical is intuitive. Forget about these set theory, extraordinary sets, and so on. Normally, even a child untaught can be can say when something flows from another, A implies B. It seems to be, and it's irrespective of language or anything else. The sense what is logical in India is the same as what is logical in the US. But I never dreamt that we could actually have a dispute of whether a paper is complete and logically without gaps for almost 8 years now, and there is no there doesn't seem to be any solution in sight. So let me talk about this problem. And this is really an incredible problem in mathematics. So the problem that I'm talking about is known as the ABC conjecture. The ABC conjecture. And it's reasonably simple to state. It's about natural numbers. So everybody knows about natural numbers. So I'll state it, though the result seems a little corny, but I'll say it. So what it says is, if I have three natural numbers, A, B, C, such that A plus B is equal to C, and suppose the GCD of A, B, C is 1, the greatest common divisor is 1. I'm using only concepts from school. There's no sophisticated maths involved in that. Yeah, so suppose I have three natural numbers, A, B, and C, and the GCD is 1. Because you see, the thing is, if I have an equation, A plus B is equal to C, if there's some common factor, I can factor it out and finally get 1 where the GCD of A, B, C is 1. Then the conjecture says that given epsilon greater than 0, there exists some positive real number K epsilon such that C is less than or equal to K epsilon into the radical. I'll explain what radical of ABC, the product, to the power of 1 plus epsilon. This is what the conjecture states. Yeah, what is the radical of a natural number? Uh, it is the um, largest square free factor of that number. So you see, by the fundamental theorem of arithmetic, if n is p1 to the power of e1, so on, pr to the power of er, where the pi's are prime, the pi's are distinct primes, right? And e1 to er are natural numbers. Then the radical of n is equal to P1 into P2 into PR. See, it ignores the powers. So this is the largest square free factor of n. And radical of 1 is 1. Incidentally, that's just radical is defined to be 1. Uh, so if n is P1 to the power of E1, P to the power of E2, so on, PR to the power of ER, where the PIs are distinct primes, then the radical of n is P1 into P2 into PR. It's the largest square free factor of n. So what this ABC conjecture says is that if I have three natural numbers, A, B, and C, such that A plus B is equal to C, and if the GCD of ABC is 1, they have no common factor, then given any epsilon greater than 0, there exists a K epsilon such that C is less than or equal to K epsilon into the radical of A into B into C to the power of 1 plus epsilon. This is an extremely powerful conjecture. In fact, it implies Fermat's-Last theorem. If we could prove this conjecture, then there is a half a page proof of Fermat's-Last theorem. All that wild stuff need be ignored. The funny thing is about this conjecture is a lot of people have been, this conjecture was made sometime in the late 80s of the last century, 1987, I think, by two French mathematicians called Osterley, Masser and Osterley. And, lots of, it implies huge number of other conjectures. It's such a powerful conjecture. It's so simple to state, but it implies conjectures on elliptic curves. It implies conjectures on various other matters. A lot of conjectures on Diophantine equations and so on are implied by this ABC conjecture. So, so there's this Mochizuki, a Japanese mathematician at Kyoto University, who in 2012 claimed that he had a proof of the ABC conjecture using something which he called Teichmuller theory. And he put it on his blog, the proof. And, the proof was so abstruse that people couldn't understand it. They just kept on wondering that, this doesn't make any sense. So then the 2018 Fields medalist, a young German mathematician, Schulz, he decided, he works in this area, number theory. So he decided to spend a week at Kyoto uh, with Mochizuki and try to understand from him uh, the proof. Uh, has it really been proved or has it not? He spent a week, spent um, another month trying to understand it, ingest it, and he said that there are some serious gaps in the proof. So there are some serious gaps in the proof, and it is 8 years now, and it's still not clear whether it's proved or not. It just shows how so he maintains that at certain points in the proof there are serious gaps, maybe even what is claimed is not true, whereas Mochizuki claims that it's true. And the thing was that Mochizuki didn't publish the paper, just kept it on his blog. I guess he was hoping to get acceptance from the mathematical community that the proof is correct. But Schutz keeps on maintaining that the proof has serious gaps in it. And finally, last year, Mochizuki published the paper in the Kyoto Journal itself, his own university's journal, of which he is an editor. And it was felt that was very unethical thing to do. So, I never believed that there would actually be a dispute on a proof, whether it's correct or not, for so long. It's at least 8 years now that this has been going on. In fact, let me mention one last thing. I have a few minutes. One last thing. This danger of working alone. This is another thing in research. It's better to be open and discuss your problems with people, because you could go wrong. I mean, after all, for that formula for Fermat primes went huge, extremely wrong. So, and the prime example of that, of course, is Andrew Wiles and his proof of Fermat's last theorem. He found out about Fermat's last theorem when he was 10 years old. And he made it his life's ambition to solve it. But of course, he had to think of his bread and butter. So what he decided was that I'm not going to touch this problem till I become a full professor at a top university. And once he became a full professor at Princeton, his PhD was from Cambridge. He's an Englishman originally. He started working on Fermat's last theorem in secrecy. And for years and years, he was not seen at conferences, anywhere. He would refuse all invitations, etc., etc., etc. And he was working on it with great secrecy, alone, not interacting with any others. And then finally, in 1994, his alma mater, Cambridge, said, look, he hasn't come for conferences, but they were having a very special anniversary conference. I don't remember what it was the anniversary of. And they invited him. And lo and behold, he accepted. And there was an immediate buzz in the mathematical world that he must have solved the problem, because he had kind of made it clear to people that till he solves the problem, he won't come out of hibernation. And so they gave him the last talk of the conference, thinking that he'd make a grand announcement. And sure enough, he made a grand announcement in the last talk of the conference, announcing that he had proved Fermat's last theorem. But the thing is, he hadn't shown it to anybody. And of course, it was a long proof, a lot of very abstract mathematics. In fact, he used the Langlands program quite succinctly. And immediately copies were made of his write-up and sent to 6 experts in the field: Barry Mazur at Harvard, Jean Pessier at Collège de France. The 6 biggest experts in the area were sent a copy of his paper. And they discovered a gap. They discovered that there was something which he had assumed was not true. You wonder how such a well-established mathematician could have made such an assumption. In any case, the gap was discovered and there was total deflation that the proof is still open. The reason why there was this deflation was because in the previous 3.5 centuries, several times people had claimed that they had solved Fermat's last theorem. And every time it was discovered that there were gaps in the proof. Wiles didn't want to be part of that list, but he actually turned out to be part of the list. And then he went back to the drawing board, and the gap that had been discovered, he tried desperately to close the gap, and he couldn't. And finally, someone said to him, look, your own student, your own PhD student, Richard Taylor, he's a professor at Harvard. He's distinguished. He's an expert in this area. Why don't you call him and collaborate with him? And he relented, and Taylor and he spent, I think, almost a year together. And that gap could not be filled. But what they did was, what they managed to do was to skirt the gap, to go around it, to give another method so that the proof becomes valid. That gap still remains. So you see, it's better to be open. It's better to discuss your problems with others, because this is huge danger that you may overlook something which may become an embarrassment. Actually, at a much smaller level, I know a colleague of mine when I was a postdoc at TIFR who was working on a problem in topology, and he didn't discuss enough with others, and finally the proof was actually published in a very good journal called Invenzione, and it was discovered that there was a gap. The proof was wrong. That there was some incorrect statements made in it. So, it's better to be open and discuss mathematics with as many people as possible. And I don't mean your immediate colleagues. It would be, you can do it on the internet. You can discuss it with anyone, anywhere in the world. Yeah, so I should give some time for questions. So I think I'll stop here. I think I've dealt with all the problems that can come up in research in mathematics. And yeah, I hope I haven't forgotten anything. Thank you very much.
Thank you, Professor Tandon, for the excellent talk. You touched upon everything required right from finding a research problem, how to do it. It's a major issue each time students come. In
Yeah,
fact, yesterday too, I was asking one of our resource persons, that it's a serious thing. Do we assign them a problem or do we give them time to decide one themselves? This was being done to us in our times, and very often and go, and very often problems are just assigned to them, and
yeah.
so thank you, sir. You discussed it in detail. You showed the beauty aspect of mathematics, how important it is, that the proofs are beautiful,
Actually, I
and
I didn't ask. I should have asked the composition of the audience. My talk was, my examples naturally, because I'm a mathematician, I use all examples from mathematics. I don't know. I try to keep it as simple as possible. I don't know how the non-mathematicians in the audience fared, but I hope by and large they could get a gist of what my examples were.
so there are some questions which are put on the chat window.
Ah,
Uh,
yes.
should I read it out or you
No,
can see
let
them?
me go to the chat myself. Yeah.
Muhammad Asif says, uh, "Sir, please ask Professor Rajat Tandon. Being a mathematics research scholar, whatever someone asks us, what research methods you are using or what research methodology you are applying, it becomes difficult for us to answer this question. So, will you say something about it?" Yeah,
Yeah,
that's
I
a good
agree with
question.
you. I agree with Mohammed. That's why I said, see the UGC, the bureaucrats over there, they try to come with a one fit all solution. They think that the same, like I can understand in a data oriented subject, uh, the question of research methods would be very important because there are ways and ways of collecting data and relevant data, there's so many things on data. So research methodology make full sense over there. But if you're doing maths, uh, oh, the only research methodology I should mention is the following. You must make a thorough, once you have a problem, you must make a thorough survey of what is known in that problem. I cannot stress this factor enough. You must, because you don't want to be finding a solution that's already there in the literature. That's number one. But I can give you an example myself of my last student. There was one question asked by a American mathematician called Savin in his paper, and I said I normally gave such problems to my student, and so he looked at another paper by a Japanese mathematician, and he tried to copy the technique over there. Okay, so my problem had two parts to it: case A and case B. Case A was done by one of the students, by this Japanese professor, and case B had to be looked at. And, you know, the Japanese professor in his paper never mentioned that case E had already been solved. And we kept on for 2 years trying to prove the case B part of it. And then suddenly we discover, hey, this was done even before the Japanese professor. So it's very important. It's very important the only research methodology I would say is be cognizant of the relevance and importance of your problem, number one. And once you have a problem, please make a thorough subject survey. Find out all that is known in that area about that problem. Otherwise, you could find yourself in duplication, or you could find yourself, in our case, trying to search for something which already exists. So that's about a subject survey on the problem that you're working on is the most important thing that you need to do.
There is another question by Muhammad Asif.
Yeah.
He says, Sir, I'm working on study of biological models. Is it possible to collect data for the models? And what is the procedure and methodology to collect data? Thank you.
Well, quite frankly, I'm not the correct person to answer this question because I know nothing about biology. I know nothing about what criteria data should satisfy in order to be relevant and correct in biology. So I would suggest that he ask this question to uh, to a biologist.
I would suggest Asif to speak to Professor Haragopal, who's taking all these sessions on statistics. He
Yeah,
has done a lot of work with life scientists and he does a lot of
yeah,
applied statistics work. So do talk to him. He will tell you exactly how to define your samples, what size they should
right,
be,
right,
what test to apply. Yes, so speak
right,
to Professor Haragopal.
right.
Then there are comments, great session, sir, from Arun Bangar, and very nice session. Thank you. So, thank you, sir, for a lovely session. Uh,
Yeah, I hope people. Uh, I just hope that everybody understood the kind of problems that I was enunciating. The problems of research in mathematics. We don't have this data problem, so we just need to meet the needs of logic. But even logic can be controversial.
Thank you, sir.
Yeah.
It was excellent. Thank you.
Okay. Thank you.